Results and visualizations. The mathematical implementation computes the steady state heat flux and total heat transfer rate using Fourier law based on the specified material properties, geometry, and boundary temperatures. The computed values are presented numerically, while interactive visualization illustrate how variation in thermal conductivity, material thickness, cross-sectional area, and temperature difference influence conductive heat transfer. The notebook provides the following output. The heat flux is expressed in watts per meter squared. The heat transfer rate is in watts. This is the energy per unit time. Temperature difference, delta T, across the material, and interactive perimeter controls for material and geometric properties. Now the sample numerical result here for the following input parameters. So given here is thermal conductivity, K equal to 205 watt per meter Kelvin. Cross-sectional area equal to 0.02 meter squared. Thickness equal to 0.05 meter. Hot surface temperature 100 degrees Celsius. And cold surface temperature is 25 degrees Celsius. So the results are, so the delta T here is 75 degrees Celsius. The heat flux here by using this formula is 307,500 watts per meter squared. And the heat transfer rate here by using this formula, so Q times A here is 6,150. So the mathematical notebook includes several interactive visualization to enhance understanding of Fourier's law. Heat flux versus temperature difference demonstrate the linear relationship between the heat flux and temperature difference. We have the heat transfer rate versus thermal conductivity. Show that materials with higher thermal conductivity transfer heat more efficiently. And we have the heat transfer versus material thickness. Illustrate the inverse relationship between thickness and heat transfer rate. And we have the heat transfer rate versus cross-sectional area. To demonstrate that increasing the cross-sectional area increases the total heat transfer rate proportionally. So interactive parameter here study allows users to modify thermal conductivity, thickness, cross-sectional area, and boundary temperature using sliders with numerical results updating instantly. So this visualization provide intuitive insight into the influence of material properties and geometric parameters on conductive heat transfer, making the notebook a useful educational and engineering analysis tool. Now for the bar chart here, so we have the given here, 75 the temperature difference, and we have the heat flux here is 307 500, and we have the heat transfer rate is 6,150. So we have here heat flux. This is equal to 307 500 watts, and we have the heat flux rate here. The length. We have the temperature difference here. The temperature difference. So this is the height here refers to the heat flux watt per meter squared. So we have here the height is also equal to the heat transfer rate here. For the horizontal bar here, using the Mathematica here, so we have the height here is the heat flux, and the height of the horizontal height of the heat transfer rate is here, given by 6,150. So we have the temperature here. Then we have the pie charts. We have the heat transfer rate is this portion of the total area. Then the larger portion here is the heat flux. So we have the gauge indicator here. So temperature difference. We have the gauge 75, the temperature difference. And the heat flux here is 307, 500 watts per meter, watts per meter squared. And we have the heat transfer rate is 6,150. And for the engineering table here, so we have the value and unit here, temperature difference 75, heat flux 307, 500 watts per meter squared. We have the unit here on the right side, and heat transfer rate is 6,150 in terms of watt. So the temperature distribution along the wall, most important here. So we have the thickness here is 0.05. We have the temperature in the hot surface temperature is 100 degrees Celsius. So as we increase the thickness up to 0.05, temperature decreases until such time that it becomes zero. And we have the interactive version. For example, if we increase the thermal conductivity here, so we have the corresponding value for the heat flux and heat transfer rate here. And if we decrease the area, we have the corresponding values. Now, if we increase the area here, so we have the corresponding value. Now, if we decrease the thickness, we have also the corresponding value for the heat and heat transfer rate, this one. Now, for the, if we increase the temperature, the hot temperature here. We can also decrease the cold temperature here. So we have the corresponding value for the heat flux and the heat transfer rate here. Now we can also increase the temperature here.